Okay, good morning. We are going to get started. Hopefully everybody can hear me. And we have a low turnout today, but that's okay. We'll cover a lot of good material. We're going to end the section on muscles this morning, and we're going to start on the nervous system. So we're tracking along right where we should be as we enter the month of April. So anybody have any questions on anything? Okay. I hope nobody's been affected by the fire so far. And just try to pay attention to the news. I just saw that the fire has tripled in size overnight. So we need to just listen to the news when we hear stuff like that. So anyway, moving on, let's get into the muscles. And the last thing we talked about was rigor, but now we're going to talk about where we get our energy from muscle contraction. See, muscles are have high energy demands. They require lots of ATP. And you know, ATP only lasts for a few seconds. So we have to keep making ATP over and over and over again. Now, when a muscle gets a signal to do something, there's always a little ATP around. You know, there's always some inherent ATP in the muscles themselves. And that'll give us about 4 or 5 seconds worth of energy. That's, you know, that's all that's ATP lasts for 5 seconds. You know, we can't store it. But there's another mechanism we use to provide energy for about 15 or 20 seconds more of activity, and that's using something called creatine phosphate. Creatine phosphate is a muscle that's found in our skeletal muscle fibers that will easily give up one of its phosphates to ADP, adenosine diphosphate, to make ATP. There's an enzyme called creatine kinase. And so we can run off of the ATP we have in the muscle already when it gets an action potential from a motor neuron, and it will run for about 5 seconds, and then another 15 seconds or so from this ATP made from creatine phosphate. Now, that's a lot of times. That's about 15 to 20 seconds worth of activity. That's a lot of time. You can do a lot in 15 seconds. If you actually look at the clock and watch the second hand go around and see how long 15 seconds is, if I were to start counting now, it's 5 seconds, 10 seconds, 15 seconds. There's a lot you can do in 15 seconds. And you're still just running off of the ATP you already had in your cells before it broke down and the creatine phosphate. But what we go into after creatine phosphate is exhausted, we go into glycolysis, the anaerobic respiration, where we're taking glucose and breaking it down and we form pyruvic acid. So that will give us energy for 30 to 40 seconds. Now we have almost a minute. And there is a tremendous amount of activity that we can get done in a minute. You can walk up a flight of stairs in under a minute. You can run out to your car in the rain in under a minute. If you watch basketball, well, that basketball is not a good, I'll get back to basketball. If you like to watch football or baseball or any sport, many sports like baseball and football in particular have periods of intense activity and then periods when nothing's happening. And they alternate. You know, in baseball, The outfielders are standing around waiting for the batter to hit the ball. The batter hits the ball and runs to first base, and the outfielders circle around and try to either catch the ball or throw it back into towards first base or wherever the play is going to be. But only one outfielder will do that, maybe two. Now, none of those plays take more than take a minute in time. Most of those kind of sports plays might be done in 15 seconds. It might be done in 30 seconds, but it doesn't last a minute. The average play in football is done in under a minute. And most of the action, most of the movement has stopped before the play ends. The movement on the offensive line or the defensive side of the line, depending on where the play's going, most of those players are not moving anymore after the play is broken out. Whether you have a receiver going out for a pass or the runner has broken free and is progressing down the field, or the punter punts the ball and everybody runs forward to down the ball. Even those plays don't take very long. Most of the activity in those kind of sports are going to be creatine phosphate and glycolysis. Now, if we move into past 60 seconds worth of energy demand, then we go into aerobic respiration, the Krebs cycle and electron transport, those horrible terms which we try to avoid saying. But that takes about a minute to get to those. We don't instantly start with aerobic cellular respiration. We don't instantly start with glycolysis. The ATP that's present in our muscle cells when we first get a signal down the motor nerve and creatine phosphate give our muscles time to spin up glycolysis. Glycolysis takes a few seconds to start up. It's not instant. So between the creatine phosphate and the ATP, you've got about 20 seconds worth of time to get ready. Plus, you may have already done everything you need to do in that 15 or 20 seconds. Once glycolysis starts, we can run off of glycolysis for activity for about 40 seconds. And then we will move into, if the activity lasts longer than 40 seconds, a minute altogether, then we will slide into aerobic cellular respiration. Because it takes time for that activity to spin up to speed so that we can start producing lots of ATPs. But a lot of the things we do don't require aerobic cellular respiration. We can get by very nicely, sometimes on just creatine phosphate, sometimes on just creatine phosphate and glycolysis. It is usually the long duration activities that are going to get us into the cellular respiration phase. So. Now, when we do engage in cellular respiration, the aerobic stage where we're using oxygen, we can be driven by that energy for hours. If we're doing, as they say here, moderate activity, you're going for a walk, you're going on a 5-mile hike, you can go very nicely for hours and hours on aerobic cellular respiration. At some point, though, we will likely have to kick back into anaerobic, because we are running, when we are using aerobic cellular respiration, we are drawing on the oxygen stored in the myoglobin of our muscle cells. As long as that oxygen is present, we're going to operate aerobically and generate lots and lots of ATP, 36 ATP per molecule of glucose, lots of energy. But at some point, we might exhaust the oxygen in the myoglobin. It's a term called oxygen debt. It occurs after you've had continuous activity in the muscle for hours, and you deplete the oxygen, and now you switch back to anaerobic respiration, glycolysis, which doesn't use oxygen. And so you now, instead of getting 36 ATP, you're going to get 4 ATP. You still have energy, but now your muscles are now suffering from what we call oxygen debt. And without oxygen, glycolysis takes a different pathway. Glycolysis normally starts out, if we got plenty of oxygen, glycolysis starts out, we end up with, a couple of ATP and some NADHs, and we end up with pyruvic acid, and the pyruvic acids go into the Krebs cycle. Well, when we are in oxygen debt, we don't make pyruvic acid, we make lactic acid. And lactic acid accumulates in our muscles. And the more lactic acid that we have in our muscles, the more painful they're going to be to move. Our muscles become very sore and tender as that lactic acid level rises. Of course, the lactic acid is also lowering our blood pH and making us more inclined to breathe faster. And because we are assuming that we're generating lots of CO2. Well, because we're acidic. CO2 combines with plasma to form carbonic acid. Well, that's not what's happening here. We're breathing faster simply because our blood's becoming more acidic. Our medulla oblongata has no clue what's causing us to become more acidic. We just breathe faster. But eventually, when we exhaust the oxygen stored in our muscles, we will be breathing, we will be running off of anaerobic methods. Now, lots of times we've experienced oxygen debt. We're not aware of it. There's no big red flag that goes up and says, oh, you're in oxygen debt. Your face doesn't turn green or something like that. With oxygen debt, you recover within 24 hours. You simply reload the myoglobin. Myoglobin is a storage pigment that's what makes our muscles red. We recover over 24 hours, and our oxygen levels, stored oxygen levels, go back up, and our lactic acid levels drop, and our muscles stop hurting the next day or the day after. So this shows you, this slide's probably slightly out of order here, but this is a really good slide to show us what's going on here. Where does our energy come from? First 5 or 6 seconds is the ATP that we had just made before the nerve, the motor nerve sent the action potential into the muscle. So we have 6 seconds worth of stored ATP, because we don't really store it. We make it and then it degrades after 6 seconds. So we use it. We have about 10 to 15 seconds worth of creatine phosphate. So that gives us somewhere in the neighborhood of about 20 seconds worth of energy from the two sources. And as I said, in 15 or 20 seconds, we can do an awful lot. Then we get about another 40 seconds worth of energy from glycolysis. That's a minute. As I said before, most of our physical activities that we engage in are over in a minute. And if we go past that minute, then we move into longer duration exercise, and we use aerobic cellular respiration with the Krebs cycle and electron transport. So we can have energy for hours. The consequences, though, are going to be depletion of the oxygen and oxygen debt, which then leads us into lactic acid accumulation. See, because as long as we have oxygen available at the end of the electron transport chain, we're going to accept electrons in the mitochondria coming down through the inner membrane. That only happens if pyruvic, to get to that stage, we have to have pyruvic acid coming into the mitochondria. Well, pyruvic acid isn't going to form at the end of glycolysis if there's no oxygen. We make lactic acid instead. And so we cut off the whole chain of Krebs cycle and cellular respiration. Anyway, so that's why our legs hurt after exercise. That's why we have oxygen debt. We're not aware of it. But when our arms and legs will hurt after exercise, it's because we have stretched the muscles. And if we've done long duration activity, let's say you go for a very long hike up a steep trail and come back down, then your muscles are sore the next day for a couple of reasons. One, because you stretch them, and two, because you have probably exhausted, all your stored oxygen, have oxygen debt, which leads to lactic acid accumulation, which causes pain. So anyway, nothing operates in a vacuum. Everything, all these systems and responses are all linked together. Now, our muscles will fatigue. Our muscles will always get tired. It's, muscle fatigue has nothing to do with ATP. We always have lots of stored glucose in the form of glycogen in our bodies to provide energy. So it's never an absence of ATP. I mean, even if we're running off glycolysis, we're still going to have lots of ATP. Usually what happens, though, is that when we reach fatigue and our muscles can't contract anymore, it's because we have some sort of problem with the level of ions present. If if our potassium levels are high, then the muscle cell is hyperpolarized. It's harder for the muscle cell to reach threshold, because if the cell has excessive levels of potassium in it, the resting potential on the charge is not minus 90, it might be 130. So now to get the threshold, you got to depolarize not from minus 90 to minus 50. You have to go from minus 130 to 50. The more potassium you have in a cell, the greater the negative, the greater the membrane potential is. So it's not if you have a hyperkalemic state, meaning lots of excess potassium. Excess potassium will drive the charge away from the threshold even further. Makes it harder to contract. You might even be in a situation where you have, you could have higher low levels of potassium, you could have higher low levels of calcium. Calcium, what do we use calcium for in muscles? Well, we use it to bind to the troponin and roll the tropomyosin out of the way. We also have to use it to open up the calcium gates to trigger the release of the neurotransmitter. There's all sorts of things that can go wrong here. So, it can be excesses, it can be losses of these different ions. And so, whether we have a lot of calcium or not enough calcium, whether we have excessive levels of potassium, if we have small amounts of potassium, if we don't have enough inorganic phosphate to make ATP, that can interfere with the whole process of contraction and excitation and coupling. So there are many things that will cause our muscles to fatigue and not work. Because of ion concentrations and other molecules in the cell. It is never a problem with ATP, because there's always plenty of ATP. Well, at least the potential is there, because we got lots of glucose. We've always got lots of glucose. So, okay, now, what about contractions? Well, we see a contraction take place. The muscle is stimulated by a action potential from a motor nerve. The motor nerve releases the neurotransmitter that opens up the motor end plates, sodium channels. The motor end plate depolarizes. That hits the threshold level of the voltage channels for sodium on either side of the motor end plate, and we know what happens after that. We produce tension in the muscle. the muscle may or may not move. Two types of contractions here. We don't always have to have the muscle move. We always have tension. We always have tension in the muscle when the sarcomeres are contracting, but the muscle may not move sometimes. Isometric contractions. The muscle doesn't shorten. The muscle doesn't shorten. We are trying to lift something we can't lift. We're trying to push something we can't push. If you're trying to push against the wall, and you're standing by a brick wall, and you're pushing on the brick wall as hard as you can, or even the wall of the classroom, you're pushing on the wall of the classroom as hard as you can, but nothing's happening. Your muscles are all tense, and you're pushing and you're straining. Your inner abdominal pressure is coming up, and all the other good things. And you're pushing as hard as you can, and nothing is happening. We don't move, as we say, we don't move the load. The tension is not great enough to move the load. The force that you're bringing to play on the wall is not sufficient to move the move the load. In this case, the load is the wall. You're pushing absolutely as hard as you can. Nothing's happening. That is what's known as an isometric contraction. The muscle doesn't shorten. The muscle doesn't contract. It becomes tense. It generates a lot of power, but it's not enough to overcome the resistance of the load. You can't push against the wall. You can't push against, you can stand in a door frame and push your hands out against the door frames on each side. You're not going to move the door frame. You're pushing against the earth. You're pushing against gravity. You're not going to move the earth. The tension that you generate in the muscles never exceeds load. However, the one that gets everything done for us, the one that we use to manipulate our environment, is the isotonic contraction. The muscle will shorten because the tension that we generate in the muscle will exceed the load. You can pick up a brick. You can pick up a book. You can push a door open. You can ride your bicycle. You can walk. All these things you do because the tension in the muscle is now greater than the force it's trying to overcome. So most of what we do is going to be using isotonic contractions. Isotonic contractions allow us to do things. And we will contract the muscle. The muscle length can shorten, or the muscle length can enlarge. Think about that for a second. The muscle is contracting at the same time it's being stretched. So we have two types of isotonic contractions. We have what's known as a concentric contraction, where this is what we see all the time. If you flex your arm, you bring your arm up to touch your shoulder, you have bent at the olecranon process. So your arm is flexed, and then you extend your arm. You pull on the olecranon process, and it straightens out. We're pulling on the radial tuberosity, we're pulling on the olecranon process, our arm moves, flexes, and extends back and forth. That is a concentric contraction. The muscle will shorten. An eccentric contraction, the muscle is being stretched at the same time it is contracting. You are pulling on that muscle and stretching it. You are stretching that muscle at the same time the muscle is contracting. It's a very, very powerful contraction that you're having here. Eccentric contractions are probably 50% more, are more powerful by 50%. Almost half again as powerful as an concentric contraction, as when the muscle shortens. But here, when the muscle lengthens, as it's contracting, it's a very powerful contraction. However, the price you pay for stretching that muscle while it's contracting is that it hurts later on. When you are hiking uphill, and then hiking back downhill, you are stretching your hamstrings going downhill. They're contracting, but they're being stretched. Your quads are being stretched going uphill while they're contracting. So they're very powerful contractions. But the next day, your hamstrings and quads are going to hurt because they've been stretched. They do their job, they contract, but they get stretched at the same time. So these are isotonic contractions, the two types, concentric or eccentric. Now, isometric contractions, we don't shorten, we don't lengthen, because we can't move the load. You can't push against the earth and win. In fact, it is the isometric contractions that hold us upright. When we're standing upright or sitting upright, our muscles are actually pushing against the earth. Like right now, they're pushing it. I'm standing in the classroom and my muscles are pushing against the floor, so which is indirectly pushing against the earth, underneath the building, but I'm pushing down. I'm holding myself upright thanks to these isometric contractions. I can't win by pushing against the building. I'm not going to move the building. I'm not going to move the planet, but I'm using that type of contraction, the tension in my arms and in my legs, to hold me upright. So the two types of contractions are isotonic and isometric. Isotonic are, anytime you move a load is an isotonic contraction. Anytime, both of these are going to generate, the isometric and the isotonic will both generate tension, but only the isotonic will allow you to move something. Isometric, you can't overcome the resistance of the load. Can't move the planet, can't move the wall. You can move a brick, you can move a chair, you can walk, manipulate your own environment, but there are some things that we can't manipulate. Something else that we encounter here, similar along the same lines here of our isometric and isotonic contractions are, did you know that we have light meat and dark meat in our bodies? Light meat and dark meat. Consider the lowly chicken. The chicken breast is light meat. The legs are dark meat. Or consider, you have white tuna and light tuna. The white tuna is much whiter, and the light tuna is sort of off-white. There's a difference in there. You have the chunk white and the chunk light. Well, that's based on the types of muscle fibers we have. Muscle fibers that have lots of myoglobin. Lots of myoglobin are going to be darker. They're going to be darker because of the presence of the myoglobin. The myoglobin is the respiratory pigment that carries oxygen. So if you have lots of oxygen in your muscle cells, you can do things longer. So the darker fibers, the darker fibers are what we call the slow fibers, not because they respond slowly, but because they give us long duration activity. They can last longer. They are resistant to fatigue because there's lots and lots and lots of oxygen there. They start slowly, they contract slower, but they last much longer. So if you are a chicken Your dark meat is in your thighs and legs. Now, what does a chicken do? A chicken spends most of its time walking around. Okay, like most birds spend a lot of their time either sitting on something, sitting on the ground, sitting on a post, a telephone pole, the wires, high up in a tree. They don't spend a lot of time flying. Now, the muscles that do all the work for them are going to have lots of myoglobin present and be fatigue resistance. The leg muscles, for example, the thigh muscles. So the dark meat of a bird is rich in myoglobin. The darker meat of a tuna fish, which is sort of redundant, is going to be rich in myoglobin. Long duration activities, fatigue resistant. Birds spend most of their time standing around. The muscles in our bodies that we use the most, like our leg muscles, for example, are going to be rich in myoglobin. They are the slow fibers. They're the dark meat, if you will. Now, the other type of fiber is the fast fiber. This is the white meat of the bird. These fibers contain lots of glycogen. So the dark fibers, the slow fibers are rich in myoglobin. The fast fibers, the white meat of the bird, for example, are high in glycogen. They can give you lots and lots of energy quickly. Lots of energy all at once. Powerful contractions, but they get tired very easily. These muscles are easily fatigued. So a bird, the muscles of the breast, for example, are what a bird uses to fly with. But if you ever watched a bird will flap its wings to take off. It will reach a certain height and then it will start gliding. It will look for thermals, up currents or an updraft to keep it aloft. And it will glide for long periods of time and rarely flap its wings, only if they can't stay in the air as long as they want. They don't spend a lot of time flapping their wings, but when they do, it's a very powerful contraction. It's a very, very powerful contraction. Same thing applies to the tuna. The white meat of the tuna occurs, is used when for short duration activities, you're swimming away from a predator, or perhaps trying to be a predator and catch something. It doesn't use it for very long. Now, long duration swimming events in a tuna, it's going to use its dark meat, the slow fibers. The same thing applies to us. Activities where we have intense action, like driving a nail, throwing a ball, some sort of short duration, powerful activity, we're going to use the fast fibers. They're going to get tired. They're easily fatigued. Oh, comment, question. Okay, that's okay. It happens. So I went ahead and marked you as here, so you're okay. So, okay, now, a pitcher in baseball or softball is only good for about maybe 70 or 80 pitches before their arm is really sore, because those are high energy demand, high energy activities. Whether you're throwing a softball or a baseball, that is a very powerful contraction. You can't keep it up indefinitely. Running is a little different. We can run for long periods of time if we need to, but throwing some short duration activity that's very powerful, muscle tires out. So areas in our bodies where we need to be able to do short duration, powerful actions, we're going to have a lot of fast fibers. You know, they're not, they're going to be lighter than the slow fibers. So they're, you know, next time you're in the store and you see, you know, canned tuna, you know, you can think of the difference between fast and slow fibers if you look at tuna. So, or the next time you eat chicken or turkey, say, oh, these are the, when you're eating the breast meat, these are the fast fibers of the bird that uses it to fly occasionally. You know, you'll be very popular at a meal if you do that. So anyway, we're almost done with muscles. 3 slides worth of important terms. A cramp. We've all had cramps. We know what a cramp is. It hurts. It is a muscle spasm that it's not a twitch. It is a spasm where the muscle gets tight. We usually tend to get them in our gastrocnemius muscle in our leg. It hurts. We don't like it. Frequently caused by some sort of chemical imbalance, you know, usually potassium. So, another term here, hypertrophy, enlargement of a muscle cell or a tissue or an organ. As we'll see in AP2, our bodies have a bad habit of enlarging structures when they don't work properly. Now, muscle cells are different. The more we exercise a muscle cell, the more protein we give it, the bigger it'll get. And that's a good thing. It'll get stronger. You know, we don't grow new muscle cells, but we can make the muscle cells we have bigger by feeding them more protein, feeding them more glucose, and the cell enlarges. That is hypertrophy, the increase in the size of the cells. We don't have hyperplasia. We don't grow new muscle cells. You know, we don't necessarily like to see an increase in the number of cells. We see that in other organs when there's some sort of problem going on. When we get into AP2, and just a pitch for the May term, AP2, registration starts up on Monday. The AP2 May term runs for 13 days, and then you'll have the whole semester worth of AP2 done by June the 1st. So if you have any questions on May term, let me know. Okay, that was my announcement. That was my advertisement for my May term class. Okay. Most of the times when our body enlarges something, it's not a good thing. It might even be a cancer. Our muscle cells only enlarge, healthy muscle cells only enlarge when we exercise and provide them with more protein. We don't grow new muscle cells. Hypertrophy of the muscle, again, we are making new, we're providing protein to make actins and myosins. We make bigger and bigger myofibrils within the cell. We enlarge the size of the cell by adding more myofibrils. A couple things that can happen. What's known as flaccid paralysis. Flaccid paralysis is a loss of muscle tone. Usually what happens is something affects the motor neuron as it's leaving the central nervous system. The signal from the brain or spinal cord can't get to the motor neuron. Something is blocking the signal. And so the muscle itself will be flabby. It will be weak. It will not be able to contract. We call it flaccid paralysis. If you were to pick up a person's arm with flaccid paralysis, it would drop right back down. And it's usually traced to something, some sort of damage to the motor neuron, the motor nerve, or perhaps damage at the spinal column and at the spinal cord, or even the brain where the motor nerve connects to the central nervous system. Now, spastic paralysis is different. With spastic paralysis, you have contraction of the muscle. The muscle is contracted, it's tight, it's held in place, it's paralysis. It's the paralysis we think of when we think of paralysis where they're immobilized. They can't move it. An individual that's had a stroke on one side of their brain or the other may have spastic paralysis, where we have triggered the muscle to contract and it won't relax. So with spastic paralysis, you have a sustained contraction. With flaccid paralysis, there is no signal going on here. And this next one leads into the cramp we talked about on the other slide. A spasm. It's a rapid contraction of a muscle. It is a twitch is one muscle cell. We generally don't see a twitch occurring naturally. With a spasm, we have lots of muscle cells suddenly contracting. And again, it usually leads to a cramp, nearly always caused by some sort of imbalance in the sodium or potassium levels, nearly always caused by an absence of potassium. Nearly always, because there is always lots of sodium available for the cell. But it could be an absence, or it could be an absence of potassium. Usually it's an absence of potassium, but it could also, there's all sorts of possibilities. It could be an absence of potassium. It could be an excess of potassium, an absence of sodium, which is really unusual, but it's possible, or excessive potassium. So there's any number of possibilities here. Yeah. Last two terms. And they're even more important terms. I even labeled them that way. Atrophy. The muscle cells shrink. An organ will shrink if it's not used. But in our case, we're talking about the muscle cells. The muscle cells will shrink if they are not working. They're not being used sufficiently. A person that has been immobilized for a year, a person that is is suffering from flaccid paralysis. The muscles may eventually atrophy. They will shrink in size. The cell numbers will not change, but the size of the muscle will shrink, and the muscle gets weaker. The muscle gets weaker, and then it shrinks more, and it gets weaker, and it shrinks more. The muscle cell doesn't die. It just becomes weaker and weaker. Astronauts in the space station often experience atrophy. We just had an American come back this week, setting a new record in space of over a year. And when they were brought out of the spacecraft and they landed, they had to be carried out very carefully because their muscles were not strong enough to support their body weight. For a whole year, they were in a zero G and a weightless environment. The force of gravity was not pulling on their body. And so we didn't have a whole lot of contractions to generate, tension in the muscle. The muscles weren't being used to fight against the forces of gravity because gravity wasn't there. And no matter what kind of exercises you do in space, you can't compensate for the absence of gravity. So the muscles get weaker and weaker and weaker in space because they don't have to work as hard. So now the good news is that you generally recover most of your muscle mass in just a few weeks. So that's the good news. Now this last term is fibrosis. This is scar tissue. If you've got a scar anywhere in your body, that is fibrous connective tissue, scar tissue. It doesn't contract. It doesn't, if it's on the surface of your skin, it looks different from the rest of the tissue around it. It's shiny. It has no hairs growing on it. It has no sensory receptors. It is a placeholder. It fills in the gap, and that's all it does. And this is what happens with when muscles are damaged. When muscles are damaged, we replace the damaged or dead muscle cells with scar tissue. They're not contractile. They don't work. So you sustain a loss in contractility in the muscle. Now, whether you exercise and work out and build up the other cells to make up for that, you're not going to grow new cells, but you can make the cells around the damaged area stronger, and you may not even notice the effect over time of what happened to you. In the heart does the same thing. If the heart is damaged, it will replace the damaged tissue with scar tissue. The heart is now 5%, 10%, 20%, whatever amount was removed, less efficient because of that. So it is scar tissue. And the more scar tissue you have in skeletal muscle, the weaker the entire muscle can be. You can compensate, but it still can be weaker. It will, you can lose a lot of flexibility with your muscle too. So anyway, that should be the last slide, and it is. Okay, any questions on muscles? Any questions on anything? Let me get out of sharing here. Questions on anything? We have, we've now finished
when does the May class actually
on
start?
bones and muscles. And I'm going to go ahead and start our discussion on the nervous system. The third lecture test is, I haven't written it, so it's not really ready to go out there yet. But the third lecture test is it will cover bones and muscles. So we can talk about that next week when that's going to show up. So you may notice that the muscle lab test opens up on Monday. And no, yours opens up on Tuesday. Yours opens up on Tuesday and stays open for a week. So we can talk about that scheduling next week too. So anyway, you have nothing due right now, so you don't have to worry about anything over the weekend. Okay, let me move out of this and get into the nervous system. This is what we called, can everybody see this slide? It says chapter 11, the nervous system. I hope. Great, thank you. Okay, so let's move into this. Now, I think I can safely say that the material that we've been looking at now started in bones and definitely in muscles has gotten a lot more interesting than cell structure and cellular respiration or even chemistry. I think I'm on safe ground saying that. It's going to get even better in this. This is a really interesting chapter. The one on the brain coming up after this is also very interesting because it talks about, we're going to see why we do things the way we do. And I'm going to have a lot of good examples here for you. So anyway, the nervous system is it's the one of two controlling systems in our body. This is the instantaneous control system. This is the very rapid, very short-term control system. It uses action potentials. It uses neurotransmitters to work. It is rapid and specific. And as far as we're concerned, it's instantaneous. The action potentials in some of the nerves in our body travel at 300 miles an hour. And considering the longest nerve in our body is only about 3 or 4 feet, that's the sciatic nerve in our leg. It's it's instantaneous as far as we're concerned. The slowest nerve travels at 100 miles an hour. But a lot of those nerves only have to travel a half an inch. So again, while it's a measurable amount of time, it is for us instantaneous. So the nervous system is one of two control mechanisms in our body. The other is the endocrine system. The endocrine system uses our hormones. It is a slower system. We'll talk all about this in the whole first unit of AP2 is all about the endocrine system. It's a chemical control system. It is slower, but its effects last much, much longer, sometimes for a lifetime. So anyway, moving back to this. Our nervous system has three parts to it. Our nervous system depends on sensory input. Our sensory receptors, both internal and external, gather information for us on sound and light and touch and pressure and pain and odors and taste and balance, as well as itch and scratch, things like that. Pressure, pain, probably said it already. The sensory receptors generate action potentials. All the action potentials look exactly the same. Just like they do in a muscle cell, all the action potentials look exactly the same. But we send those action potentials from the sensory receptor, which has no idea what's going on. The sensory receptor is just being stimulated by some sort of internal or external stimulus. It's just responding to the stimulus. It's not doing anything as far as interpreting what's going on. A light switch doesn't know what's going on when it's turned on or turned off. All it does is go on or go off. It doesn't say, hey, look, the lights are on now. You know, I did that. So anyway, sensory input. The sensory receptor responds to a stimulus. It will send an action potential down a sensory neuron to the brain or spinal cord where we process that information. We can process those action potentials so that we understand what's happening. It's called integration. We interpret the results and we have something called perception. We have awareness of the stimulus. Then we can respond to it. And the central nervous system will send a signal out on a motor nerve to do something. You walk into a dark room. Your eyeballs collect light rays. Your eyeballs you're not seeing a whole lot of information in the room because it's dark. So your first thought is to turn on the lights. So you process, the absence of light is detected by your eyes. You may see things very dimly. You're processing that information. Your nervous system says, I think we need to turn on the lights, and it sends a signal down, an action potential down a motor neuron to your hand, and you throw the light switch and the lights come on. That is how we process information. Sensory input. Sensory input or a lack of sensory input tells us we can't see very well. Now, the eyeballs have no clue what's happening. All they're saying is, well, most of my photoreceptors aren't responding to anything because apparently there's not enough light to stimulate them. That lack of information is also being processed in the central nervous system and giving us a response set. Here we see, visually, that's sort of redundant. Here we see visually. Here is a visual representation of the nervous system. You see a glass filled with some sort of fluid. Your eyeballs the photoreceptors in your eyeballs are stimulated by the image, by the light rays coming off the glass. Those action potentials go into the brain and spinal cord where it gets processed. You're aware of it. Now you have perception of the glass and the fluid, and the brain says, well, pick up the glass and take a drink. So three parts to it. They all have to work together. Neither side, neither the input or the output has any clue what's going on. Its perception only occurs in the brain and in the spinal cord. So our nervous system has two key parts. We have the central nervous system, which is the brain, and the spinal cord. Everything else is in what we call the peripheral nervous system. All the nerves that feed into the brain are called the cranial nerves. And all the nerves that feed out of the brain are the cranial nerves. The cranial nerves have a sensory and a motor side. The spinal nerves have a sensory and a motor side. So we have spinal nerves to and from the spinal cord, cranial nerves to and from the brain. The optic nerve is a cranial nerve. The sciatic nerve is a spinal nerve. The optic nerve is part of the peripheral nervous system. It's one of the cranial nerves. The sciatic nerve is also in the peripheral nervous system. It's one of the spinal nerves. I say the optic nerve is a cranial. Yeah, optic nerve is a cranial nerve. Sciatic nerve is a spinal nerve. So we have nerves feeding into and out of the spinal cord, nerves feeding into and out of the brain. Only the brain and the spinal cord are in the central nervous system. Everything else is the peripheral system, because that's how, integration, perception, and control take place in the brain and the spinal cord. Signals coming in, signals going out are what we use the peripheral system to do for us. So the central nervous system is the brain. It's the brain and the spinal cord in the dorsal body cavity. The inside the skull, inside the spinal column itself. It is our command and control center. It allows us to respond to sensory input. It also takes into account whether or not we've done this before. It takes into account reflexes. It takes into account current conditions. What does all that mean? Well, you're driving down the road and the car in front of you steps on its brakes. The brake lights flash. So what is your response to do? Well, you have a couple of choices. You can ignore the brake lights and drive on into the back of the car. You can press on your brakes and slow down to match the speed of the car in front of you. Or you can turn off at the first intersection to get away from this car that's driving 20 miles below the speed limit. Or I guess you could ride up behind it and start flashing your lights and say, get out of the way or something like that. That's an option too, not a good option. So your response to the person in front of you putting on the brake lights, applying their brakes, is based on your past experiences, your reflexes, and the road conditions. It is a dark, rainy night, and you're driving down a narrow road, and the car in front of you applies their brakes and slows down. And because it's a wet road and it's rainy and visibility is poor, you see the brake lights flash and you go ahead and do the same thing. So that's probably there's probably a reason for that. Perhaps there's a 2-foot deep puddle, a large puddle, probably like a lake-sized puddle across the road. We've seen a couple of those recently. How do you respond? You go on previous experience. You go on your reflexes. Your reflexes, the light comes on, the brake lights come on, and the learned reflex you have is to take your foot off of the gas and put it on the brake. So you can slow down to match the speed of the car in front of you. Current conditions play a lot of, current conditions play a big role here too. Now, what about a yellow light? We've all seen yellow lights. You know, in some places around the country, yellow lights and red lights are considered options and not laws. You know, yellow light in the textbook answer, what do you do when the light turns yellow is slow down and prepare to stop. That is the textbook from nearly every driver's manual in every state. Slow down and prepare to stop. However, it doesn't take into account things like, well, I'm 100 yards away from the traffic light and I know this light and it turned yellow, and by the time I get to it, it will turn green again. So do you slow down and stop 100 yards away? Do you drive up to the light? Do you slow down a little bit because you know that if you wait, if you drive through it, approach it, it's a 5-second light or something like that, you can go on through. Do you race up to the light and try and run the light before it turns red? So you're in the intersection while it's still yellow, so technically you went through on a yellow light? Or do you just go ahead and drive on up to the light and apply your brakes and stop? What do you do when the light changes? There's a whole lot of situational events that have to occur. Are you right behind another car? Well, obviously, if they're not going to go through the light, you're not going to go through the light. Is there a law enforcement officer behind you? That will definitely dictate what your response is going to be. Is there one sitting on the side of the road? Is there no traffic? Is it 3 o'clock in the morning and there's nobody around? Are the roads wet? Are the roads icy? Are your tires good? Are your tires bad? All these things are stored in your central nervous system, which are going to dictate your response. They're going to dictate what you're going to do. We all, you know, we every time we do any kind of action, it's going to be different than the one previously. Next time you drive down the road and the light turns yellow, are you going to go through it or not? Well, if it turns yellow and you're right practically underneath it, yes, you're going to go on through. It's not safe to stop. That's always been my argument. If it turns yellow and you're 100 feet away from it, there's nobody in front of you, you may see, well, maybe I can get up to it, and if it's still yellow when I get to it, I'll go on through. Or you can not be in a hurry and just go ahead and stop when the light, you know, says prepare to stop, because it's going to turn red on you anyway. You know, so you have a number of options, but what do you do when the light turns? You know, this is not the Parkway, but some days it feels like the Parkway when all the tourists come to town. How do you respond? What kind of decisions do you make? Usually, you know, we try to make good decisions, but sometimes we make poor decisions, or we see poor decisions. You know, every opportunity to go through a traffic light is a decision-making process. We have to take into account all the different conditions going on there. We don't think about it. You know, when we're driving, we usually drift off into driving land, you know, and that's, you know, we set sort of like we go on autopilot and we're driving, and, you know, we've got other things that we're thinking about, and yet we're doing just fine, because one part of our brain is taking care of the driving and another part of our brain is thinking about what we're doing later in the day. Now, this is a bad decision. This could have been a bad decision here. The individual in the middle of the screen, the minivan ran 2 red lights and almost hit the car that was crossing on a green light. Well, you know, it's easy to be distracted. You know, we don't know what's going on inside the minivan, you know, or they're just not paying attention. Here's another decision-making process that was pretty poor. Again, someone is driving along and doesn't catch the red light. It can be accidental. It can be deliberate. This person will remember it because the traffic cameras went off and caught them running through the red light. I think it's in Florida. I think that might be outside Jacksonville, Florida. It's an interesting intersection anyway. That's the only thing I can say in defense of the driver there. And they didn't, well, they were speeding too. So now, the one at the bottom is pretty interesting. This is a very poor decision-making process. It involved an innocent bystander, because you'll notice how the car, we have two cars speeding. The car coming towards us in the picture ran the red light from the other direction and got hit from the side, and then they all plowed into the car with the camera in it. The one at the top on the upper right side here, this one, 5 o'clock in the morning, 4:52 a.m. in January of 97. I even forget where I found this on the internet, but you can see it's still dark. You can see that you have that the car on the left T-boned the car on the right. You can see the light's red. You can see, because up here, there's the red light. There's the red light right there. Now, traffic camera catches this. What you notice behind the driver is a child in the child seat back here. So someone's distracted. They drive through a red light. It's early in the morning, and it's easy to become sort of dulled to the surroundings. Again, a poor decision-making process. And yet all the information we need to make a correct decision is there. But the conditions of the day, the conditions of the road, the conditions of the car, the conditions of the driver, all affect that. Just because we have all the information we need doesn't mean we use it. Okay, and I'm sure that we've all been there, driven through yellow lights that turned red, driven through red lights accidentally, driven through stop signs. It happens. It just happens. It's not like we deliberately go out to do things like that. Okay, moving on. The nervous system, the peripheral system, and the central nervous system. First of all, let's take a look at the peripheral system. The peripheral nervous system feeds into the brain and spinal cord and takes information out from the brain and spinal cord. There is a sensory side, which is the afferent side. Action potentials come in from the skin, from our muscles, and from our joints. Proprioceptors tell us what's going on. Touch and pain and pressure receptors tell us what's going on. Itch and scratch and pressure and heat and cold all send information in. So the peripheral nervous system is feeding information into the brain and spinal cord. Also from the viscera. Does my gallbladder hurt? Does my appendix hurt? Is my bladder full? Things like that. The visceral fibers. Sensory input, all action potentials coming into the brain and spinal cord. The motor side, the output side, takes signals out to what we call the effectors. They can be muscles, they can be glands. So the motor side will send action potentials out to tell a skeletal muscle to contract, or tell a smooth muscle to contract, or tell a gland to release some fluid, or to stop releasing some substance. The motor side has two parts to it. It has the somatic side, which is our motor nerves. Skeletal muscle motor nerves are the somatic tissue. We control when we have voluntary muscle contraction. We raise our arm, we lower our arm. That's somatic motor nerves doing that. Motor nerves output from the brain or spinal cord. The other division is the autonomic system. That is totally involuntary. We don't have to think about processing food in our belly because it's an autonomic response. The autonomic nervous system tells the smooth muscle around our stomach to churn and churn and churn when there's food present in there to be broken down. It tells our small intestine to squeeze this process, this digested food, this mixture of digested food and stomach chemicals down through the small intestine so we can absorb the nutrients. The autonomic system tells us to constrict our blood vessels near the skin on a cold day so we don't lose body heat, or tells those same blood vessels to relax on a hot day so we can radiate heat away from our body. We don't have to think about autonomic responses or autonomic actions. They just something we don't think about. You know, it's totally involuntary. Somatic is voluntary, autonomic is involuntary. And if you like flowcharts, here's a really busy one for you, but you can see the breakout of the two areas. Central nervous system is actually pretty easy to say, well, it's the brain and spinal cord. Okay, that's the central nervous system. The peripheral system gives you the cranial nerves, the spinal nerves, and those are broken out into sensory and motor. Then we're done with sensory, taking information to the brain and spinal cord. Motor goes out in two pathways: somatic to skeletal muscle, voluntary, or autonomic to smooth muscle and cardiac muscle, involuntary. And then we have one more division of the autonomic side. We have what's known as the sympathetic division, which is the fight or flight side. And we have the parasympathetic side, which is the rest and digest and defecate, and everything is nice, you know, and relaxed. The sympathetic division is fight or flight, hurry up, let's do something really quick right now. So, and they, needless to say, these two, the sympathetic and parasympathetic, are antagonists. So I think I've said most of this already. Somatic side controls skeletal muscle. It's under voluntary, it gives us voluntary control of skeletal muscle. The autonomic side, we have the visceral motor nerves. We regulate our smooth muscle, our cardiac muscle, all of our glands. It is totally involuntary, and it is made up of the sympathetic and parasympathetic sides. The parasympathetic side is the dominant side. The rest and digest and defecate side is the dominant side. The sympathetic side only comes into play when we go into a fight or flight mode. So if we take a look at the nervous system, let's take a closer look at the types of tissues we deal with. Now, in nervous tissue, there are two types of cells. We have the what we call the glial cells. Remember on that picture of the neuron way back at the beginning of AP1 lab, and you saw the big neuron and saw these little purple dots, tiny little purple dots around it. Those are the glial cells. They do the heavy lifting in the central nervous system. They protect the neuron, they surround the neuron, they feed the neuron, they repair the neuron, they destroy the neuron when necessary. And of the glial cells in the central nervous system, we have four different types. We have what are known as astrocytes, microglial cells, the ependymal cells, and what are called the oligodendrocytes. The other type of nerve cell are the neurons. The neurons are going to be the ones that send that are going to receive sensory input and generate action potentials that go to the brain or spinal cord. So we have glial cells and neurons. There's a whole lot more glial cells than there are neurons. So the most common type of all glial cells are the astrocytes. They're called that because they're shaped like a star. Now, astrocytes will wrap themselves around the neuron. It will wrap themselves around the capillaries that are supplying the neurons with nutrients, glucose and oxygen. They will wrap themselves. They also create what's known as the blood-brain barrier, so that things that we don't want to enter the neuron won't come out of the capillary. They prevent certain types of medication or certain types of drugs to go to leave the capillary and go into the neuron. So it's a way to protect the neuron. It also holds the neuron in place. It helps to hold the neuron together or in its correct location. You can see here the big yellow structure is the neuron. The red structures are the capillaries, and there's the astrocyte shaped like a star. There are more astrocytes than there are any other type of glial cell, and their role is to protect the neuron, hold it in place. They can allow the transmission of glucose and oxygen into the neuron. They do a lot of the heavy lifting so the neuron can survive. The microglial cells. Microglial cells are the macrophages, the phagocytes of the central nervous system. They protect the neurons. When a neuron is injured, it will help the neuron to repair itself if it can. If not, it will help the neuron to destroy itself and eliminate and remove it and take out any kind of debris. So, because some there is a limited amount of repair functions that we can do with our neurons. They are the protective cells of the central nervous system. The ependymal cells, the third category of neuroglial cells in the central nervous system, they line the cavities within the brain and in the spinal column. They generate cerebrospinal fluid, and they have cilia to move this fluid around. And this fluid will bathe all of the central nervous system cells, and it's constantly moving. It's not very much fluid. It's under a liter in here, but it's constantly moving through the brain and through the spinal cord and all around. And then the last category of the central nervous system are called the oligodendrocytes. The oligodendrocytes are going to insulate the actual neuron and the axon of the neuron. The axon is what the neuron uses to send an action potential to the brain. And the axon is insulated with a fatty protein called myelin. And so it wraps itself, the oligodendrocytes wrap myelin around the axons. This allows the speed of transmission of the action potential to be much, much faster. This is where we approach 300 miles an hour to go 3 feet because of the insulative properties of the myelin around the axon itself. So, okay, and that is a great place to stop. We will pick up on Tuesday, starting out with the peripheral nervous system and look at its glial cells. So let me get us out of here. Anyone have any questions? Okay, then I'm going to get us out of here, and I hope you all have a great weekend and stay safe if we have that fire issue going on.